Hello. Today we will be discussing the sustainability in material sciences and how a material selection steps will give us an achievable sustainable solutions further. Uh, as we have seen over the past century, material consumption has skyrocketed with the use of materials for energy, packaging, and products, increasing by at least 20 times per capita. In highly industrialized nations since the 19th century, this rise has led to a significant strain uh, on our environment as well as economy as well as our society. We are now facing critical issues related to resource utilization, whereas the pollution that we can see, and only a small percentage of these materials and energy required for production are actually used in the final product. So, a significant portion is lost during production, transportation, and disposal, particularly. So, for non recycled products. Additionally, even if companies were to reach a zero emission today, the earth would still feel the effects of the emissions that have already been released. So, further, we have breakdown on how a sustainability will help us in the material selections, like importance giving to the balancing conflicts objectives that the sustainability would provide, energy efficiency, economic and social benefits, as well as what all metrics that we can see here is uh, the environmental metrics that we have calculated, and economically and socially how it will present. Now coming to Stuti, who will be talking about balancing conflicting objects and the energy efficiency that we would see.
So we are focusing on the material selection steps, and these are the material selection steps and things we'll have to keep in mind while selecting materials. Uh, on the left, we've included a complete funnel-like structure where we go through three processes. We're defining first the project requirements and applications. Then we are evaluating the material properties, and finally we are going to to how the material is processed, and we're understanding the functional and the performance needs. On the right of the screen, you can see the different indexes or things we can keep in mind while selecting materials so that we can achieve sustainability. One is the resource depletion index. Then we have the life cycle assessment, in which we evaluate each and every point in the life cycle. We have the durability, recyclability, social impact factors, economic impact factors, and technical impact factors. So if when we look at all of these factors, then on a whole, we'll be able to select a material that's eventually sustainable. We'll now move on to the life cycle assessment, and first evaluating the environmental impacts of the material selection steps. We'll move on to the economic and the societal impactors later on. This is the life cycle assessment that we've made for any industrial material. The life cycle assessment process is basically a systematic method for evaluating the environmental impact of a product or a service through its life cycle. So we'll be going through each and every step of the life cycle and seeing what all resources are used and what all emissions are there. Uh, life cycle assessment is a very common way to measure sustainability that can help consumers, policymakers, and businessmen make more informed decisions. So, first of all, we have the raw material and processing step. This is where we begin. As the extraction and processing of raw materials can have significant environmental impacts, for example, mining and drilling can lead to habitat destruction and pollution. Then we move on to polymer production stage, and in between all these stages, we have the transportation stage where fossil fuel is constantly being used and the greenhouse gas is being emitted. We have the polymer production stage. So the raw materials are sourced, they are converted into the polymers after this, and this stage often involves energy intensive processes that obviously contribute to greenhouse gases and wastewater emission. We then have the processing and the conversion stage. After the polymer production, materials are processed and converted into the final products. So we have the conversion of raw material into product stage. All of these involve the emission of greenhouse gas and wastewater. We have the final product use, in which the use phase is where the product serves its intended purpose. However, it is also important to use in a cradle to grave life cycle assessment the disposal stage as well. So we reach the disposal stage and the end of the product's life. Disposal methods such as landfilling, composting, biodegradation, all these result in the emission of greenhouse gas, and we also get energy through this. Jayesh will now be covering the plas- uh, bioplastics versus plastic comparison and the different sustainability metrics that are finally benchmarks for making a sustainable product.
Hello everyone. My name is Jayesh Krishna Prasad, and we'll be focusing on the comparison between traditional plastics and bioplastics as a part of our agenda of this project. This comparison is a crucial topic in the context of sustainable material selection. As we know, plastics have become an important part of our daily lives, but the environmental impact is significant. So, we will explore the greenhouse gas emissions, land use, energy demand, carbon footprint, water footprint, and economic factors associated with both traditional plastics and bioplastics. Understanding these differences is essential for making informed choices that promote stability and sustainability. Okay, so first we'll start with traditional plastics. So, the greenhouse gas emissions, which we can see, generate the traditional plastics generate these from 18,000 to 1800 to 2500 kg of CO2 equivalent per ton, and this high level of emission contributes significantly to climate change. Coming to land use, the production of traditional plastics requires approximately 500 to 1000 acres hectares of land per ton. This land use can lead to habitat destruction and loss of biodiversity. Energy demand. The energy required for producing traditional plastics ranges from 70,000 to 90,000 megajoule per ton. This high energy demand often relies on fossil fuels, further exaggerating environmental issues. Water footprint, again a major problem. Traditional plastics have also considerable water footprint, which adds to the strain on our freshwater resources. Water footprint, to reiterate, is the amount of water used in the production of traditional plastics. Now moving on to the advantages of bioplastics. So first of all, the greenhouse gas emissions. Bioplastics typically have a lower carbon footprint with emissions ranging from 500 to 1000 kg of CO2 equivalent per ton. This reduction is crucial for mitigating climate change. Coming to land use, the land use for bioplastics is similar at around 500 to 1000 hectares per ton, but the sourcing of raw materials often involves renewable resources which can be managed sustainably. Energy demand, the energy required for bioplastics is significantly lower, ranging from 50,000 to 55,000 megajoule per ton. This reduction in energy can lead to lower greenhouse gas emissions during production. Now coming to the economic factors, since we since sustainable development not only involves taking care of the environment but also seeing if the process is economically feasible, the initial cost of bioplastics may be higher, but their potential for recycling and lower environmental impact can lead to long-term benefits. Now, the metrics for sustainable material. So this is the final goal of our project. So in this, we'll be discussing the key metrics for evaluating sustainable materials as outlined. Understanding these metrics is crucial for making informed decisions in material selection, especially in the context of sustainability. So first, let's talk about energy demand. The metric here is set at 50,000 megajoule per ton. This figure is aligned with the recommendations from the International Energy Agency, which emphasizes the need to reduce energy consumption through technological improvements. By selecting materials with lower energy demands, we can significantly decrease the overall environmental impact associated with the production and use. Next, we have waste metric, which is targeted at 0.2 kg of waste per kg of material. This aligns with the principles of circular economy, which advocates for waste reduction through recycling and remanufacturing. By minimizing waste, we not only conserve resources but also reduce the burden on landfills and the environment. Then, carbon footprint. The goal is to limit emissions to 1000 kg of CO2 per ton of material. This target is based on the commitments outlined in the Paris Agreement, which aims to limit global warming to 1.5 degrees Celsius. By focusing on materials that meet this carbon footprint metric, we can contribute to global efforts in combating climate change. The water footprint is another critical metric set at 10,000 liters per ton. This figure is recommended by the Water Footprint Network, which emphasizes sustainable practices such as efficient irrigation and water cycling. By selecting materials with a lower water footprint, we can help preserve our precious freshwater resources, which are increasingly under threat. Lastly, we have the land use metric, which is set at zero point 0.5 hectares per ton. This target is based on best practices in sustainable agriculture and land use efficiency, as suggested by the Roundtable on Sustainable Biomaterials. By minimizing land use, we can help protect natural habitats and biodiversity, ensuring that our material sourcing does not come at the expense of environment. In conclusion, these metrics for sustainable materials, energy demand, waste, carbon footprint, water footprint, and land use provide a comprehensive framework for evaluating the sustainability of materials. By adhering to these guidelines, we can make more responsible choices that not only benefit our projects but also contribute to a healthier planet. Thank you for your attention. We hope this comparison helps you understand the importance of selecting sustainable materials in our daily lives.